It's now 2 minutes past the hour, so I think we're going to start. I just wanted to welcome everybody to the AI Winter School being organized here at Brown, available remotely, recommended for graduate students, postdocs, advanced undergraduates. We really appreciate you joining us this morning. We're going to be presenting 6 different modules from different area of physics. You will be able to see all of the details on the Indico link that you all have. Now, there were just a couple of technical issues I wanted to make sure you understood, which is that all the material for this course is being provided via Google Drive. So you need to register with an email address that is Google capable so that we can get you access to the material. If you've registered with an address that appears to have that you can't use for being given permission to access Google material, could I suggest you re-register with a new address? Just go through the registration process again and use either an address you already own or create a new one, a new Google address that you just use for the conference. It does help us to have your other email address, but just re-register a second time. This will just make sure that you're able both to access lecture and support materials, but also we want you to be able to run our very specific Python notebooks that are made available under the Google Colab. That's COLAB, the Colab Python system. We're going to be using that to really help you run the demonstrations. It uses Google's remote service for free, and it's very easy to use, but it does require you to have to have a valid Google a valid Google account. So please make sure you do that. Okay, that was really the admin. I think I'm going to pass over to my colleague now, Greg Landsberg and Lucas Gorskos, who are the 2 people that are going to be running this next session over the next 2.5 hours. Thank you so much.
Thanks, Rick. I believe actually yesterday Sean opened Google View access to the world, so you don't even have to be registered to be able to copy things from Google Drive. But definitely registering is needed for collab, as you say. Right. So, well, my name is Greg Landsberg. I'm professor at Brown doing particle physics, and Lucas Kuskas is my colleague who will basically run the exercises, and I'll give you the lecture. The title of this talk is Unsupervised Anomaly Detection in Particle Physics. And here are some pictures on how to say, tell the difference between a muffin and a dog, which might not be trivial for a machine sometimes. Also, how to synthesize different images. Here you have an image of a cat, which is actually looks like a poodle. So all these cute things could be done using unsupervised learning, and we are going to talk in many detail about that. But before actually going into the unsupervised learning, I want to talk a little bit about general search methods, or I didn't finish the outline, but I don't really need it, and tell you a little bit how we do searches when you physics in particle physics, which is the raison d'etre and the main reason for the Large Hadron Collider. We are actually am now at CERN near Switzerland, near Geneva, Switzerland, why it was built. First of all, let's talk about the search concept. Generally, one searches for a specific signal with certain properties in a sample composed of a mixture of this potential signal and the background. This is a classical hypothesis testing statistical problem, which has been solved a century ago. And it is the common solution to this problem is known as maximum likelihood method. One could also treat in a different way uncertainties in the various systematic uncertainties in addition to statistical uncertainties in the maximum likelihood method. And there are several different techniques such as profiling, nuisance parameter integration, etc. We won't be talking about that. We'll be focusing on machine learning aspects of the search. Search analysis typically deal with the situation where the hypothetical signal is much less than the background. And that requires the analysis optimization. If you just look at the raw spectra, you won't be able to see the signal because it's typically overwhelmed by the background. There are different ways of optimizing signal versus background, and people use various figures of merit, or FOMs. For instance, the most common one for large statistics searches is the Gaussian significance, which is given by the ratio of the signal, expected signal, to the square root of the sum of the signal plus background. So if you maximize this thing in the Gaussian case, you would maximize sensitivity of your search. There's also modified Gaussian significance, which takes into account the systematics, and this is this formula where B is modified by adding the variance of B squared. There's a so-called Ponzi significance scheme, etc. For the low background cases, it's important to actually use Poisson significance, which is usually done by maximizing the expected signal significance with the Poisson statistics. And of course, whenever you optimize something, you should really optimize for best sensitivity for the signal rather than for the best exclusion for the signal, because the point of every search is to find something and not to set limits. You only set limit if you fail to find something. So while in the Gaussian case, the discovery and limit-based optimizations typically give the same optimal points. This is no longer true for the Poisson case. And if you start optimizing for a limit in the Poisson case, you might actually miss the signal, which is obviously not good. Okay, so we started this business many, many years ago in particle physics. And of course, with the advances of statistical method and more powerful computers and various packages, visualization and data analysis packages, our methods of searches increased quite dramatically in sophistication. If you look at the papers in particle physics circa 60s and 70s, mostly people would use so-called rectangular cuts. So a rectangular cut in the two-dimensional plane is illustrated on the figure on the bottom left, and you see some distribution of the background in red, some distribution of the signal. In blue, there is some overlap. And if you just try to use rectangular cuts, meaning x1 greater than something and x2 greater than something else, you would end up with a rectangle, which is shown with the black lines here. And clearly, this is not the most optimal way to discriminate signal from the background. If, for instance, you correlate x1 and x2 and do something a little bit more sophisticated, like a diagonal cut, you would see much better signal to background ratio or the signal significance by doing the green cut, meaning cutting everything away below and to the left of the green line. But even the cuts which fully decorrelate two variables are not necessarily the best one. For instance, let's look at more synthetic example, top right, where a signal is a circle in blue, which is surrounded by the background, which has a shape of a donut. Clearly, it's a very artificial example, but this just drives the point. So if you try to optimize things with rectangular cuts, you would get something like the black box as your optimum signal selector. And of course, this is not the best one, because if you transform yourself into polar coordinates with the origin of the polar coordinate system at the center of the two concentric circles, you could separate signal and background with 100% efficiency by simply cutting on the radius in this polar coordinate system. And this becomes a true optimal cuts. Of course, this is a classical example where you could use a machine to optimize rather than doing it yourself. Especially, it's easy to visualize things in 2 or maybe 3-dimensional space, but it's fairly hard to visualize your selections if you have multi-dimensional space with 20 or 30 dimensions, which is fairly typical these days for searches because you try to really uncover tiny signals under fairly large background. So in this case, people actually used already in the 90s of last century multivariate analysis techniques. And one of the simplest multivariate analysis techniques is random grid search, where you take, say, simulated background events and simulated signal events, and then you just use individual events to pick a point in the multidimensional space, and then you loop over all the events and find the point which gives you optimal figure of merit of the separation of signal to the background. A more sophisticated approach is to use multivariate techniques where you use nonlinear relationship. And classical example of this type is either neural nets or boosted decision trees. And neural nets are typically trained on a mixture of simulated signal events and background events in such a way that you essentially try to maximize the output of the neural net, the discriminant of the neural net, D, to be 1 for signal and close to 0 for the background. And if you do so, you get optimal separation between signal and background. In this example, the neural net at the constant discriminant value would give you some complicated nonlinear contour in the plane of signal and background, and that is the optimal cut. The artificial neural nets essentially approximate the way our brain works by numerically solving a set of nonlinear ordinary differential equations, which is done by training of the net. And they typically consist of some input nodes. These are the variables which you select to try to discriminate between signal and background. And then there are several layers of hidden nodes where all these nonlinear processes happening. And finally, you output this discriminant. This is the simplest case of a single neural net which discriminates one signal against one background. You could imagine more complicated configurations. And these neural nets have been implemented in major statistical packages. For instance, there's a TMVA package in Root. Root is the Soren data visualization system, which we often use in particle physics, which allows us to analyze data, store data, and then visualize data by displaying various distributions. All right. So what are the boosted decision trees? Well, boosted decision trees are based on recursive binary trees. You sort data in each input variable. These are x1, x2, and so forth. And for each variable, you find an optimal split value. So you ask whether I should take the events where a certain variable is above a threshold, and you optimize for this threshold. For the next node, you select the variable and split value that gives optimum separation. And if no improvement in separation can be achieved by further splitting, the node is a terminal node and the exit from this boosted decision tree algorithm. And these above steps are applied recursively, but in reality, a single boosted decision tree is not a very powerful classifier. And we boost the performance of this classifier by creating many random trees and weight them according to the separation power. This is known as random forest. In the training of each tree, we use some new events and some events misclassified by a previous tree. That's how we do the boosting. So if the first tree is not capable of classifying some of the events correctly, we feed the sample of these events in the other tree and hope that the other tree would be more efficient in separating these events. And this is all done semi-automatically. There's a powerful libraries for boosted decision tree The most commonly used one is XGBoost, which is a Python library in which you could use standalone way. The performance of a multivariate algorithm is often characterized by a ROC curve. ROC came from World War II. This is the term which is acronym for receiver operating characteristic. And essentially, this was invented during the World War II to basically to classify the efficiency of radars to identify enemy objects such as aircraft, tanks, versus some background objects. And they are used to compare the performance of various algorithms and to set working points for a specific algorithm, where you could specify a true positive rate, which is how efficient you are in identifying the signal, versus a false positive rate, which is how often you misidentify background for the signal. And as you see on this plot on the right, the closer you are to the top left corner in the performance of the ROC curve, the better you classify. A perfect classifier would be given essentially by a dot in the upper right corner, which means that it has true positive rate of 100% and 0% false positive rate. In reality, we never approach perfect classifier, but you see that the blue curve is doing significantly better than, say, a green curve, which already does better than the yellow curve. And if you just look at the diagonal, which connects the lower left and upper right corner, this is the performance of the random classifier. You randomly choose whether to call an event signal and background, and you get efficiency and false positive rate the same, which defines this diagonal. So, of course, any signal selection algorithm should be above this random classifier and hopefully approaches the perfect classifier. Good algorithms typically have the area under the curve, which is the basically integral of this ROC curve from 0 to 1, greater than 90%. So what you see in blue is the classifier with area under the curve about 95%. Only 5% of the area is above this curve. Now, the advances in CPU and particularly GPU allow to take artificial neural nets to quantitatively new level, which we call deep neural networks, or DNN. They effectively are just more complicated ANNs. They contain a large number of hidden layers, resulting in billions or sometimes even trillions nodes, which allowed for a qualitative jump in the performance, things which were not possible with shallow networks with low number of nodes. Actually become walk in the park for these deep neural nets. And that's why artificial intelligence and machine learning became everyday thing rather than something esoteric which people use for specific tasks, typically in science. Now, human brain contains about 80 billion neurons and about 150 trillion synapses. And DNNs these days actually overperform human brain in terms of the complexity. For instance, ChatGPT-4, the latest version of ChatGPT, contains 170 trillion tunable parameters. So this is more than number of synapses in the human brain. So in principle, it would really outperform a human. The basic idea of deep learning is to minimize the so-called loss function over a set of parameters using some nonlinear function which is encoded in this neural network, and optimization of the neural net approaches the best solution from the point of view of optimization of maximum likelihood. The machine learning in the past 10 years really exponentially increased the use of the machine learning in particle physics. And this is a slide which was shown at one of the major conferences we have in the field, which shows all different type of machine learning and all different applications in particle physics. And the codes you see, like this 9 or 10 digit letters, 2304 and so forth. The first two numbers is the year when this specific paper was submitted to the archive depository. And you see that most of these papers have 22, 23, 21 as the year. So most of this development really happened, is happening in real time and happened in the last few years. You see only a handful of work which dates back to 2019 or 2018. Most of them are really happening in the few years. And you see that the landscape is quite large. And what we're going to talk mostly about today is this blue blob, unsupervised learning. And specifically, we'll talk a bit about use of unsupervised learning for anomaly detection. So the neural nets are really amazing tool for many areas of particle physics, in particular for identification of different particles. A typical question we asked before we could do the analysis, whether an object we see in a particle detector is an electron or a jet. And sometimes jets look very much like electrons. So you could try to train a deep neural net to figure out whether an object has certain type, or if you just look at the jets alone, you may want to ask yourself, what is the quark content of this jet, what this jet was originated by, whether it was a gluon, a light quark like UD and S quark, a charm quark, a bottom quark, or maybe even the heaviest of all, the top quark. And this deep learning based algorithm by now outperform dedicated taggers, which based on theoretical consideration. This is really a solved problem. There is no doubt that machine does better than human brain. Just by throwing this problem on a huge neural net with many, many different parameters outperforms any theoretical basis tagger, which uses matrix elements or some theoretical calculations to try to improve the separation between different classes. It has a very well understood performance because essentially we have infinite samples of different kinds of jets or different types of particles available at the LHC. So we could test we could train neural net on one sample, test it on completely different statistically independent sample, and make sure that all the things which could be pitfalls for machine learning, such as overtraining or picking on wrong features of the data set, are eliminated. And that really allows us to do very well. This is a plot from one of the reviews, which I reference at the bottom, which shows, for instance, that particle net, the deep graph network, which was largely developed by my co-runner of this session, Lucas, was really giving the best performance in terms of rejecting the background versus tagging the jet of a certain kind. So let me try to minimize the thing. I'll switch from the screen mode, full screen mode for a second, because I cannot minimize the window with people, which doesn't allow me to see full slide. So the particle net here is basically the line which you see on the very top. This is a rock curve, and you could immediately see that particle net has the highest area under curve, which is very good. It's a little hard to say what it is because the y-axis is in a log scale, so it doesn't look like the log curves graphically on the previous few slides, but it has a fairly good performance. I think it's around 84% area under curve or something like that. However, neural nets, they are clearly very amazing tools, but they could be very dangerous if they're used as black boxes. It is critical to have representative and large training samples, especially for deep neural nets, who often have billions or even trillions of trainable parameters. And it's important to avoid the overtraining of the net, where you pick on specific features of trained events and which are not necessarily representative of the full sample, or to avoid sculpting. Neural net could actually sculpt some of the distribution, creating artificial peaks like mass peaks, which you could fool yourself thinking is a signal. Even complicated neural nets can be opened up. This is one example how you could actually visualize one of the networks where the size of the nodes is proportional to the importance of the feature, and the thickness of the line is also proportional to the importance of the connection. So you see that in this specific example, the node, which is given by the large green circle on one of the output layers, is connected mainly to the variable known as MT, which is so-called transverse mass, which tells us that MT has large separation power between signal and the background. So modern tools allow you to make graphs like that and actually see which variables are most important for the neural net. And you could simplify neural net by removing the variables which do not help your performance. And there are semi-automatic packages which allow you to do this as well. Now, we talked about use of the deep neural net in particle ID, but using them in the analysis is a much more debatable issue, because unlike large training and test samples which are available for particle ID purposes, there is only one reincarnation of the analysis. You cannot repeat the same analysis a million times on different statistical samples to make sure that the neural nets are not overtrained. And the main question which you would need to answer if you want to prove that your analysis is done properly is, how do you know that this deep neural net hasn't picked on some artificial feature of, say, simulated signal samples, or maybe it picked on something which is due to imperfect simulation. For instance, lack of high-order Feynman diagrams in specific Monte Carlo generator, which you use to simulate the signal. The other issues which you need to address is, how do you know that DNN is stable against small changes in the architecture? If you change a little bit the number of neurons in one of the layers, you don't expect the output to change dramatically. Things should be more or less perturbative in terms of small changes to the architecture. And it's not so easy to prove that performance is correct with simulation, especially if you work with very large background rejection, say by factor of million, which is often needed, because you become very sensitive to any non-Gaussian tails in any of the distributions of the variables which you use for training this neural net. So DNNs in the analysis should be used with abundance of caution and with a lot of cross-check to avoid false discoveries. And here is one real-life example of rather poorly optimized analysis, which actually was published. So it's a real-life example. This is not anything synthetic. This was a complicated search for some hypothetical particle in high multiplicity final state in a model which had several types of new particles. So signatures were very complicated. It had multiple jets. Some of them were jets originating from big quarks. And the authors chose a DNN to optimize signal against the dominant background, which comes just from quantum chromodynamics production of jets, which is the major background at the LHC. And they, of course, were aware of the problems such as mass sculpting. So they put a lot of attention to make sure that the neural net does not learn somehow artificially the mass of the signal from the training sample, which might create an artificial bump in the application of this to data, even if there's no signal in data. And then when they opened the box, when they looked at the data after optimizing everything on simulated samples, they saw a rather surprising result. You see it on the right. So this plot shows you the expected limit for this specific model. This is given by the dashed line. and the so-called Brazilian flag around it, the green and yellow lines represent the 1 and 2 standard deviation of the expected limit. So 68% of the cases you expect your observed limit to be within the green band, and only in 5% of the cases you expect your observed limit to exceed the yellow band. And you see that their limit is above the yellow band, essentially across the entire mass of this hypothetical particle plane. And it exceeds 2 standard deviation. In some cases, it's nearly 3 standard deviation. And not only they couldn't exclude this specific model, you see that theoretical prediction is everywhere lower than the observed line. But also, if what they see is a real signal, they have absolutely no sensitivity to the mass. So the analysis was designed in such a way that a 500 GeV new particle would give you exactly the same output of the DNN as a 1 TeV particle. This is not a good design, not a good optimization, because this is optimization essentially which was trained to give you the best limit. If they didn't see this fluctuation, they would have set a quite nice limit of around 600 something GeV on the mass of this hypothetical particle. That's the intersect of the dashed line and red line of the theoretical cross section. But not only they didn't exclude anything, but they didn't even provide any information where to look for this phenomenon if the success is real. And that's kind of one example of how DNN is not particularly well used in the analysis. This brings me to a concept of lookout sphere effect, which is also important. And this is essentially the effect of multiple trials, because when we do searches at the LHC, we look at more than one distribution, we look at many distributions, and the more places you look, the higher is the probability that you see n excess just from a simple statistical fluctuation. So let's do an example. If one rolls a dice, a probability to get 6 is 17%, 1/6, if the dice is not loaded. If one rolls 3 dices, a probability that any of them will have 6 face up is 1 minus the probability that it's not 6 cubes, and this is 42%. So if you roll 3 dices, the probability to get the outcome you want is 2.5 times larger than if you roll a single dice. And this ratio of 0.42 to 0.17 is known as the trial factor. Similarly, if one looks for a signal in multiple search regions, the local excess, which you see, which could be characterized by Gaussian p-value, it needs to be multiplied by a trial factor in order to get the global p-value of the excess. And this trial factor is usually estimated with pseudo experiments, where you just repeat the experiment with simulated data using different simulated samples every time. But there are also some analytical asymptotic methods on how to estimate the trial factor. And if you're interested, I give you a reference here. So therefore, the more search regions one has, the larger the trial factor is, and the lower the global p-value is compared to the local one. And consequently, the so-called model-independent searches, which have been attempted at various colliders at the LHC by both Atlas and CMS, and earlier the Fermilab Tevatron by D0, which look at many, many different places trying to find an excess against the standard model predictions, are inherently less powerful than model-specific searches, because the model-specific searches, when you know exactly what signal you're looking for, you could properly optimize your search regions without paying the large trial factor price. And this also become important with deep neural nets, because neural net itself could bring in some trial factors due to its complicated architecture and also the various samples used for training this neural net. One example of lookout sphere effect, which usually are very pronounced in high resolution channel, essentially send the entire theoretical world on a wild chase of something which never existed. This is an infamous particle which was called X750, which basically was just a statistical fluctuation. And the fact that both Atlas and CMAS had an excess around the 750 GeV right here, basically people thought that if two experiments see the excess at the same place, there's no Lucas-Berry effect, because if Atlas saw it at 750 GeV, one could just look at CMAS at 750 GeV and remove any trial factor. This is, of course, incorrect, because the fact that Atlas saw it at 750 GeV doesn't preclude that it could have seen it at 900 GeV, 2000 GeV, or any other value. And since you see how quickly the observed limit fluctuates around the expected limit, which is because this is a diphoton channel which has very high resolution, so the width of these statistical fluctuations is proportional to the resolution. You could see that actually the Lucas-Berry effect is quite large, and for instance, the highest point of excess in Atlas, which had nearly 3 sigma Gaussian significance, after this trial factor turned in something like 0.1 sigma, which is essentially 0. And this is important to keep in mind when you do searches for new phenomena, because it's easy to discover something which doesn't exist due to these statistical fluctuations, which are enhanced by a large trial factor. Okay, so now let's move to real meat of this talk on the machine learning aspects, how to supervise the machine to properly do the background and signal separation. This is a typical problem in particle physics, and essentially it's a problem of uncovering a subtle signal in large background sample. And this is also a classical anomaly detection problem. We are trying to find anomalous, namely signal-like events, in a large pool of non-anomalous or background-like events. And the most powerful way of separating the signal-like and background-like events is the fully supervised machine learning algorithm. Supervision essentially means labeling. That means that we have a training sample with the events, which are a mixture of background events and signal events, and we know a priori which events are signal and which events are background. For example, if you use Monte Carlo generators to generate these events, you know when you run a signal process and you know when you run the background process. So one exposes a machine learning algorithm to a set of training data with these labels, which could be signal, one type of background, background 1, background 2, etc. And as Neyman-Pearson lemma tells you, the most powerful discriminant based on a set of observables X is the likelihood ratio, Lx, which is a conditional probability of seeing the outcome X given the signal, over the conditional probability of seeing the outcome X given the background. And a fully supervised machine learning classifier is built to approximate this likelihood ratio formula by using the known labels. For instance, background, which could be the union of all different backgrounds and signal. So machine learning is just a fancy version of any other optimization technique, where it is used to find a classifier H that is monotonically proportional to the likelihood ratio. If you maximize the likelihood and you have a classifier which is monotonically proportional to the likelihood, you also maximize this classifier. So the classifier does not have to be exactly the likelihood. You could multiply likelihood by 2. You could square the likelihood. They still would be good classifiers, because the maximum of likelihood would correspond to the maximum of such a classifier H of X. So machine learning, if you think about this, is just the numeric way of solving the optimization problem, maximization of a likelihood. In practice, the way we do it, we define the loss function, which is numerically minimized. An example of loss function is MSE, or mean squared error. This is an analog of chi-square statistics. So the likelihood ratio, the loss function for the MSE is defined as the mean of the difference between your classifier and the indicator function, taking over the signal events, where indicator function in math statistics is equal to 1 if the argument is true and 0 otherwise. So if the event on which you event number I is a signal event, the indicator function is going to be equal to 1. And if the training event is a background event, the indicator function is equal to 0. One could show very easily that if you minimize the MSE, this is equivalent to maximization of the likelihood. This is for the same reason why chi-square is just the, if you take the Poisson likelihood and take a logarithm of it, you would find that maximum likelihood is equivalent to the chi-square approach, and that's why MSE also works as the good loss function. There are other loss functions which are not so trivial. For instance, the cross entropy loss function is defined in a different way, but again, one can show that it essentially approximate the optimal likelihood ratio classifier if you have large enough training sample, flexible model parameterization, and a good minimizer. So these are the basics of the supervised ML approach. Essentially, you try to maximize the likelihood of a signal over the likelihood of your observation being due to the background using machine learning technique, using the loss function instead of the maximum likelihood ratio, and optimizing this loss function by minimizing this loss function essentially through numerical training of the neural net. But what if you're not confident about labeling the training sample? This could happen when backgrounds come from control sample in data with potential signal contamination. In some cases, one cannot trust simulation to simulate the backgrounds because backgrounds are very complicated and they might not be properly simulated by our techniques due to the lack of high order calculations or some other things, or detector performance on these events cannot be fully simulated. So often the backgrounds actually come from real sample in data. And sometimes it's just impossible to find a good sample where you have a pure background without possible signal or pure background of a certain kind. In this case, we deal with a mixture of, say, signal and background events, and we are not exactly sure about the labels. So let's consider two processes, M1 and M2, that mix signal and background events linearly with the following probability density function. The one PM1 of X is some constant F1, P of X given the signal, plus 1 minus this parameter F1 times the probability of X given the background hypothesis. And we define same for M2, except instead of F1, we use another constant F2 with the constraints that F2 is less than F1, and both of them are constraints between 0 and 1. So F1 is essentially a fraction of the signal in your sample, and 1 minus F1 is the fraction of the background. If F2 is less than F1, the sample 2 has less signal contamination than the first sample. Now, instead of S and B labels, we only know M1 and M2 labels with known signal fractions. So we know which sample we used, whether it was M1 sample or M2 sample, because these are statistically different samples. So we could label events as M1 and M2. And it turns out that one could still learn optimal H in this case if you know F1 and F2, and if F1 and F2 are significantly different to avoid degenerate cases. A possible loss function which we could use to solve this problem is the essentially loss function shown here. And one could easily generalize this for the case of more than two samples. You could define sample 3 with F3 and so forth. And one could show that if we maximize this function, essentially this is equivalent to finding the optimal age for the sample where you know exactly the labels of signal and the background. And this is the idea behind the so-called classification without label, CWOLA, which is pronounced koala. And essentially, instead of modifying the loss function, we simply use fully supervised machine learning algorithm to train the classifier to distinguish M1 type from M2 type. And it turns out that remarkably, this optimal classifier is also distinguishing signal over the background. And we could show this just by looking at the loss function for labels M1 and M2, representing them through the probability of X given S or given B. And you see that this loss function is essentially proportional to it's monotonically increasing with the likelihood of S over B, as long as F1 is greater than F2. And it's easy to check that if you differentiate this likelihood M1, 2 over DLSB, it's always greater than 0, which means that it's monotonically increasing with the increase of the likelihood. So if you maximize L M1, M2, this is equivalent to maximizing L as B. The beauty of koala approach is, unlike in the previous example, one does not need to know what F1 and F2 are, as long as you know that F1 is greater than F2. And this is quite remarkable because even if you don't know what fraction of the signal could contaminate your sample, for instance, because you don't know what the cross-section of some hypothetical signal is and how many signal events to expect, as long as you could find the sample which have different expected fraction of signal contamination, even if you don't know them precisely, this weak supervision, the koala technique, allows you to find optimal separation between the signal and the background. I'll skip some performance things. So this brings us to the concept of unsupervised learning. Given the success of weakly supervised learning, it is very tempting to try to optimize the search for an arbitrary signal. After all, if I didn't need to know what the fraction of the signal is in my training sample, maybe I don't even need to know what type of signal I'm looking for. Unfortunately, this is not mathematically possible, as was shown by same guy Pearson in the 30s of last century, because it turns out that only likelihood ratio, namely likelihood of signal plus background over likelihood of background, or likelihood of signal over likelihood of background, possesses well-defined properties. Individual likelihoods, L of B, essentially change properties under the transformation of variables. So that means that if you try to optimize for an arbitrary signal, you basically try to reduce the background without any knowledge of what LS plus B is, depending on whether you optimize, say, in transverse momentum of certain particle or the square of this transverse momentum, you yield completely different results, which obviously is nonsense. And this is unfortunately largely underappreciated in the HEP community. And every few years, there's another attempt to reinvent the wheel and do totally model independent optimization, which we now know is simply mathematically impossible. The latest attempts, of course, use machine learning. So what can be done in this case? How can we do the machine learning, which is fully unsupervised in the sense that we don't really know how the signal might look like? What can be done is what is typically done, for instance, in searches for supersymmetry. You create a large number of independent or partially overlapping search categories. We call them signal regions, and look for the maximum excess of events over the respective background prediction among them. If you use a large number of the signal region, you're likely less sensitive to a specific type of signal you're looking for. But of course, you are paying the look elsewhere effect trial factor by having large number of these search regions. Alternatively, one can simply search for anomalies in data using unsupervised machine learning based on background dominated samples. And that's what we are going to talk about until the end of this lecture. So what is the machine learned anomaly detection? Well, unsupervised machine learning approach does not use labels at all. It is based on learning the probability of observing set of data given only the background, and by using the large sample of background dominated events, either from simulation or from data. And then it simply focuses on the cases of PXB much less than 1. The most common approach to learning this probability density function, PXB, currently involves the data compression, which essentially eliminates rare feature from the background dominated sample by focusing on the region of moderately large PXB. So even if your background sample has small contamination of the signal, if you compress information enough, you most likely won't be biased by these small contamination of the signal. And you could always check this by injecting a small amount of signal in your trained data and make sure that your technique is robust against the small injection of the signal. This makes it a very powerful tool to identify anomalies in a sample that contains potential signal, because we could then focus on the events with very low PXB. And essentially, by doing this, we reduce the background by any amount we want. So we focus on the events which do not look like background events. It doesn't guarantee that what we'll see is signal. It still has all these problems of violating Pearson theorem. It's very hard to probabilistically understand what's going on, but you could combine this unsupervised detection with a real ways of looking for signal using the other technique. And that might actually work. And I'll give you some of this example on how this is done in real life. The powerful tool to achieve this data compression, which learns most important features about the background, is the so-called concept of autoencoder. What is the autoencoder? Well, autoencoder is essentially a lossy compression algorithm based on machine learning. The architecture of a typical autoencoder is shown on this slide, and you have some input X. Then you have several layers, typically a dense neural net or some other type of neural net, convolutional neural net. And then you have the latent layer. The rest of the autoencoder is the decoding function, which essentially mirrors the encoder. So the latent layer is the bottleneck in this network. And you could start with millions of features, such as properties of some objects in the collision event. But your latent layer might be just a two-dimensional latent layer. It might be very, very simple. It might just have a couple neurons. So you compress the information from the input, multidimensional input X, in a low dimensionality latent space. And then you decompress it and you get the new set of observables, X hat. And the idea is that you train these autoencoders so that X and X hat are as close as possible to one the other. If you learn how to do this, that means that you have effective way of encoding information to low dimensionality latent space and then decoding it to the full dimensionality space of feature. So let's look at some of the examples on how these autoencoders look like. A simple autoencoder essentially is very similar in principle to the principal component analysis, which transforms features into the direction of maximum variance. For instance, if you have a blob of events in variables x1 and x2, which you see on the left graph, the principal axes are PC1 and PC2, which basically resemble the large semi-axis and small semi-axis of an ellipsoid, and you could rotate x1 and 2 into PC1 and PC2. And the simple autoencoder with linear encoding and decoding function essentially does this principal component analysis. The more complicated autoencoders, which do not have linear activation functions, which could have nonlinear activation functions, do a more sophisticated job, but it's still in principle similar to PCA. So here is the example of autoencoder with deep architecture, which uses nonlinear encoder and decoder functions. Sometimes these layers could be convolutional networks. This is often used for image processing or image compression. And the typical loss function used for the autoencoders is the either squared error, MSE, or cross entropy, which in this case is defined as shown here, where x tilde are what is shown as x hat on the plots. So you you minimize the loss of information when you go from x to x tilde or x hat. Sometimes people also add visualization terms to the loss function to make sure that networks are stable. One such visualization term is known as the sparsity condition, which essentially requires that only a small fraction of hidden layers neurons is activated. And this is useful, for instance, for classification tasks or to learn specific statistical feature of the training data set. And you see on this example that unlike the principal component analysis, which is linear, autoencoder would find the path of maximum gradient, which is nonlinear. In this case, it's the green curve versus the red line, which principal component analysis would give you. There are many different applications of autoencoders apart from the anomaly detections. Some examples include denoising. You take the image which has a noise added in, you encode it, and you decode it, and magically noise is gone. In fact, this will be one of your exercises, hands-on exercise. We'll do such a autoencoder. They're also very often used in lossy compression of images, a la MPEG or GIF compression, although these are not based on machine learning, but you could do it via machine learning techniques. This could also be used for data generation, and we'll talk about this for one of these hands-on exercise. We'll generate data, and also feature extraction and classification, which also will be one of your hands-on exercise. One particularly interesting class of autoencoders are known as variational autoencoders. This is a special class which is widely used for feature extraction and data generation. One could think about variational autoencoder as a regular autoencoder whose training is regularized to avoid the overfitting, where the latent space has actually good properties that enable the generative process, meaning that two points in the latent space would correspond to two similar features. And this could be achieved by using a special loss function when you essentially deal with the training of the autoencoders, and by essentially using the technique where you encode a single input not as a single point in the latent space, but rather than a distribution with no parameter in the latent space. And in practice, typically a Gaussian distribution with the mean mu and RMS sigma is used for the encoding. The fact that you map a single point to a distribution guarantees that two points with similar features would overlap in the latent space because these distributions would start overlapping. And the regularization term, which is added to train these autoencoders, is based on the so-called Kubic-Leibler or KL divergence, which is very often used in machine learning approaches, which essentially is a measure on how much one statistical distribution P is different from another statistical distribution Q. And this formula gives you the definition of KL divergence, where little p and little q are just probability density functions for distributions of big P and big Q. In practice, one usually uses dense networks for encoding and decoding, and typically people use the reparameterization trick by by replacing Gaussian with arbitrary mu and sigma with a Gaussian with a mean of 0 and sigma of 1, variance of 1, and then transforming one Gaussian into another through this linear equation. And the log function the loss functions for these outer encoders is typically a sum of the reconstruction loss, which is, for instance, cross entropy, and this KL divergence. It turns out that for two Gaussian distributions, G mu sigma and G01, the KL divergence, the integral could be taken analytically, and the KL divergence is given by this formula where you sum over the points. And by minimizing the loss, which is sum of the reconstruction loss and this DKO loss, you essentially make sure that your latent space has good properties so that it could allow morphing. So this is exactly what is used for image generation. You train out an encoder, and then you take a random point in a latent space and run decoder on this point to find a new image. And this new image may be not anything you trained this autoencoder on. So this is how you could generate, say, portraits of people by sampling a large number of faces in the population and then generate people who actually do not exist using some average facial features. This is how the image of the cat, which looks like a poodle, was generated on the first slide. So basically, we'll learn a little bit about variational autoencoder during the hands-on exercise. And since I'm nearly out of time, I basically want to finish with a couple examples of how this unsupervised learning was used in real experiments in particle physics. I actually have several examples in the talk, but I'll focus just on one example, which shows you how to avoid this problem of optimizing against the unknown signal, well, for the unknown signal against the known background with unsupervised search. And by the way, this figure from variation autoencoders is something which you generate yourself through the hands-on exercise. So what you see on the left is actually the picture of the latent space where you train the autoencoder on a large sample of handwritten written digits from 0 to 9. So there is so-called MNIST dataset, which has very large collection of handwritten digits with different scripts, with different slanting, and so forth. And you see that these different digits from 0 to 9 are clearly separated in different blobs in this latent space. And if you take a random point in this latent space, you could start generating digits which look more like existing digits, but also something in between. For instance, in the middle of this diagram, you see something which resembles both 9 and 3, but it's neither nor. So this is exactly these generative aspects of the autoencoders, whereas in the areas where the blobs are not overlapping, you typically get something which looks very much like the images on which you trained. And this is a classical example of generative approach, how you generate digits from the latent space by taking random points in this latent space. So back to the anomaly detection. Now when we learned a great deal about the autoencoders, how we practically use them for unsupervised anomaly detection to avoid this Pearson theorem pitfall. Well, essentially, what it means is that we focus on events with low probability of coming from the background. And then we augment this with proper statistical analysis with a given signal, which allows us to optimize, essentially, properly optimized some signal against the background. But the way we use unsupervised anomaly detection is simply to remove large chunk of the background. So we increase the purity of the sample as the first step through the anomaly detection. And then as a second step, we do the search with supervised techniques, for instance, which allow you proper statistical interpretation. And one example of this is what we are trying to do at Brown, namely anomaly detection of features of the jets, which may not be caused by known sources, may be caused by some new physics. Jet is essentially a product of hadronization of quarks and gluons, which are abundantly produced at the LHC. And the typical picture of the jet you see here on the left. And in fact, I just found out that you could buy a poster from Fine Art America, which has CMS display, probably violating every single copyright of Soren. And you could put it on the wall if you're interested. Only for $20, you could have a jet. So these jet anomalies could be caused by some new physics or some detector malfunction. But essentially what we want to do is to find the jets which don't look like regular jets from QCD processes. So this way we could train out encoder on the properties of ordinary jet and then apply them to jet in data and look at the jets which have very low probability, which we'll call anomaly score, to be originating from the background. And then we can try to use these jets for something. For instance, we could look for detector malfunctions from these jets, such as death channels inside the calorimeter of the particle detector or something else. And the way we could actually understand that our anomaly detection does the right thing is that we could first apply this technique to known anomalies. For example, jets coming from big quarks, which have displaced tracks and secondary vertices, which typically are not present in the QCD jets. Or we could apply them to jets which are results of decays of highly Lorentz boosted objects, like in the middle plot here, where two jets from individual decay products overlap in a one bigger jet, and this jet has a distinctive substructure. It has two kind of centers of gravity rather than a single center of gravity. And you could have a mixture of this case. For instance, you could look at boosted decay of the boosted Higgs boson in two big quarks. And in this case, you would have doubly anomalous jet because it has both two centers of gravity and these displaced tracks and secondary vertices. And just to show you, and essentially the idea would be to progressively add the known anomalies to the training sample until we run out of all the known anomalies, and then let our encoder to run on the collision data and find the events which do not look like ordinary jets. And then one could either construct dedicated search by examining feature of these events, or one could identify some malfunctions in the detector and be used in real time as the data quality monitor tool. So the first things we did is training the autoencoder on these jets from QCD and then applying them on jets from the decays of boosted W boson. You see that the W boson jets have two centers of gravity, this blob on the left, and light jet has a single center of gravity. The middle set of plots is your typical input jet, and then the decoded image of this jet through the autoencoder. And then if you look at the anomaly score between, say, W jets and QCD jets, you clearly see that the W jets are recognized as anomalous because the pink distribution is much wider than the blue distribution, which is the jets typical to the training sample. So that's an example how autoencoder would look for anomalies, although it never was trained on W type of jets. It nevertheless recognizes them as being different from the jets on which it was trained. And one example of this search for view search, which was just published last summer by the Atlas collaborations, is essentially the search where they look for two-body resonances in final states which has at least one lepton or photon and at least one jets. So what they did, they look at different configurations, say invariant mass of a lepton and a jet, or photon and a jet, or two jets. And some of these jets may be even identified as B-tag jets and B-tag. So this is a fully unsupervised search, which uses the so-called rapidity mass matrix, which is a certain way of parameterizing kinematic properties of leptons, jets, and photons in the event. I won't go into detail of this, but essentially it uses either Lorentz invariant or close to Lorentz invariant variables, which makes sense because basically, we expect that new physics does not depend on the boost of the system. So if you train your network on variables with good Lorentz invariance properties, you make the network much more robust. And essentially, the chosen matrix was had a size of 36 by 36 with a few elements set to 0. And that was nearly 1,300 inputs, which were fed in the autoencoder, which contained two hidden layers of 800 and 400 neurons and a latent space of 200 neurons. So the dimensionality reduction was about factor of 6. You go from 1,300 inputs to 200 dimensionality of the latent layer. Then you train on 1% of randomly selected collision events, and you apply this autoencoder to 99% of the events. And if you do so, you see the distribution of anomalous score, which is shown on the bottom left. So it's an log plot. So you see that most of the events have anomalous score, which is low. Here, the anomalous score is defined as a logarithm of the reconstruction loss, and reconstruction loss is the mean squared error between the input variable and the output variable of the autoencoder, just as an example we discussed. And by looking at this distribution, one could cut on the value of this anomaly score. Um, at certain levels, they chose to cut at about -9, which happened to correspond to effective cross-section of the events above this region of about 10 picobars. So you would be sensitive to signals which have cross-section of the order of 10 picobar. But they also considered a more restrictive regions. If you cut at 8, -8, you get to something like 1 picobar signal cross-section. And if you cut even harder, you get to 100 femtobar cross-section. So by changing this cut, you could look for more and more rare processes by reducing the backgrounds by many order of magnitude. And at the bottom, you see how different new physics models, hypothetical new physics models, look in this anomaly score. And in general, you see that they have longer tail in the anomaly score compared to the data which is dominated by standard model backgrounds. So how do you transform this to a real distribution? Well, you select a cut on the anomalous score, and then you look at the invariant mass distribution of these different pairs of objects, and you look for any bumps in this distribution. So the right-hand plot is the input to a fully supervised search for signal. You inject a signal, and you see how much signal you could inject at any given mass in order to not violate the data. So this is a fully supervised search because you inject specific type of signal, and essentially you don't even optimize against the background. You just find the largest signal you could still add to the background in order not to violate the observed data, and you set the limit on the signal strength or on the signal cross-section by doing this. And that's precisely what they did. They set the limits on the various type of resonances which could decay in a pair of jets or a pair of jet and a photon or a jet and a muon. And the largest excess out of these many areas is found at in the invariant mass of jet and muon, and it's just below 3 sigma. But since you looked at so many places, the trial factor is quite large. So the global significance of this excess is less than 2 standard deviations. So there's no indication of new physics, but that's an example how you could combine the unsupervised anomaly detection with the fully supervised search and use the first step as just a very strong background reduction tool. And I guess I'll stop here. I'll give you a few pointers to the various articles on the machine learning. You could access all of them. You see that most of them are very recent, 2020, 2022, or 2023. And you have more pointers in the handout for this course. And that brings us to the exercises. So at this point, let's take any questions and then let's make a 5-minute break and then work through a few exercises using the Python notebook. Thank you.
Greg, thank you very much.
Don't be shy. Please just ask questions or raise your hands. And I'll go from the full screen mode to the other mode so that I could see the questions.
We did have one question concerning videos, which is, yes, we will be making videos available from the talks and the workshop exercises. They will be available as soon as we can, edit them and get them posted back up again.
Good, thanks. Don't be shy, guys. Questions? Everybody is keen to try autoencoders themselves. All right, now think about, in this next 5 minutes of a break, think about some questions. If you have them, when we come back, let's do this. And I'll stop sharing at this point. We could stop the video and then in 5 minutes, resume with the hands-on exercise. I hope by now you all have account which is compatible with Google Colab. And what you need to do is to go to the Google Drive. In fact, maybe I should just share my screen and show you what needs to be done. So this is my screen of the Google Drive. This is AI Winter School, and you need to go to the folder Unsupervised Learning for Anomalies. And there you find my talk, module summary, which Lucas and I worked on, which has a little more information and some more references. And then 2 Python notebooks, autoencoders and anomaly detection, which you should copy to your own Google area because you don't have write access to this Google Drive. You only have read access so that people do not modify the code for everybody. So what you need to do is to copy these 2 Python notebook to your own Google Drive. You could do it by using actually organize and then move, or make a copy and move it to your area. And then in 5 minutes, we'll run the exercises, and you try different configurations, autoencoders, and things like that. This is not very CPU intensive, so you should be able to run all of this on GPUs without running over the free quota of Colab. So at this point, let me stop sharing and let's have a 5-minute break and resume at 11:25, I guess.
Thank you, Greg. So there is one question I see somebody posted concerning what was the LLP loss function you introduced.
Right. So let me try to answer. Need to find it.
It's under the Q&A option in the
Yeah. I saw the question. I'm just finding the right slide and sharing it. So this loss function, oh, I'm sorry, I forgot the squares. So this loss function really should have squares here. This is just the MSE, minimum square function. So now it should be correct. So you basically take the first sample and you minimize this thing. So this is just like the F1 is a fraction of the signal. So you try to minimize the difference between your prediction and the signal over the events in the first sample. And you do exactly the same for the second sample. So it's really just a MSC summed over the two samples. And the reason it's called LLP, I don't really remember. It's an acronym for something. But it's not long-lived particle, it's something else. So let me have a sip of water and be back in a minute.
So if anybody's having any access issues, there is a Slack link on the front page of the Indigo conference site. If you go into that Slack, just follow the link, register, you'll see there are people ready to help support you if you do have sort of access issues. Just again to repeat, the easiest way that is going to work is you just make sure that you're using an email address that allows associated with it does allow you to link to the Google Drive system and also Google Colab, COLAB Colab, which is this Python notebook free service, which we're going to use to allow you to sort of get a very easy access. So you want to make sure that the email address that you have given us does allow you to run under Google Colab as well. Re-register if it turns out that you've used an email that isn't that valid for accessing Google services, then just re-register again, and we'll make sure that you get access. Also, use the Slack link. Come onto the Slack and use the registration channel, and we can react to that immediately. Okay. I hope that will ease any technical issues you're having.
There are a couple questions I see on the chat. So yes, so there was one, the square will go inside the summation. Yes, that's correct. I think I typed the changes too quickly. So I'll double check the formula and put a new PDF with the correct formula. And Slack link is on the very top. I could copy it again if people want. So here is the Slack link.
So Greg, it's available at just see
Just in the overview. Yeah, I see it.
It's on the conference front page. Yeah.
All right, so maybe we should move to the exercise. We will do a few things. Lucas, you want to take over?
Sure, yes. Hi, also from my side. So I think we should start with the autoencoder part.
Yeah, I think let's start with autoencoders, do a couple exercises.
Yeah, let me try to share my screen. Rick, okay, yeah, now I'm host, so I can share. So, can you see
Yes, we see your screen quite well.
Okay, perfect. I can plug
So the
my.
way we organize this, all the tunable parameters are in the first block. So you only need to modify first block unless you want to do something a little bit more sophisticated, like changing the architecture. And
Yeah, and one thing is that here we use datasets that are available, on the internet. So it's not using jet physics related for various reasons, and also to make the exercise simpler and easier to run during the limited time we have. But nevertheless, the techniques and the tools and the conclusions are, you can transfer in any kind of problem that could benefit from these approaches. So what I would suggest actually is to start. I mean, the students, if they are, unless someone has issues to open the notebook, so this is just out. Otherwise, I think we can start running the notebook. So you can either click on, on this. You can see my pointer also, right? So
yes,
you
we
can
see your
click on
pointer. You
this.
need to connect to the runtime though.
Yeah. Sorry, because now I have the Zoom window here, and let me move it. So let me stop it. So we start from the first. So let me see. Okay, I see the message. I see a few messages here. Okay, nothing is then access. Need to register. So is
So we
everyone?
just send the instructions, I think.
Yes,
Hmm?
we'll deal with those questions, Lucas. You focus on your.
Okay, so yeah, I'm trying to keep us, to have a look at the meeting chat also. So, the first thing is to start. I mean, as Greg said, here we set the main parameters. For instance, we have an image, so we have to define a pixel size. So here we use a size that is the same between the X and Y dimensions of the image. So since it's the same, if effectively the original dimension is the multiplication of this parameter here, 28. So we have 28 times 28, 784, and we want to encode it in a dimension of 32. So yeah, there are notes here, so you can also follow them after the exercise if you have questions. So I'm not sure how familiar you guys are with Keras, but here is how we import the original image. And I think we can start with a simpler. I mean, Greg in his talk described quite a few of the options that we have to develop the autoencoder and the decoder part. So I think first we can start with a simple option, which is a dense network. So effectively, it does linear transformations effectively, but there are also other options. This is a single layer. We have also the sparse option, which I think Greg mentioned, adds some robustness on the training, so it doesn't use all neurons. We have a multi-layer perception, so we actually stack several layers, so several linear transformation. Then we have the convolutional neural network. So this, you run a convolution paths across the image to identify features in the image. And then we have the variational autoencoder, which is effectively with Greg discussed, we have a functional form and to capture the features of the image. So let's start with a simple one. I assume, yeah, this is also if you want to include noise in the samples to disturb a bit the images, give a more difficult problem. Other options is how many epochs we run. So a epoch is actually how a full, how to describe it, when we a full training, like a full pass over the network we define. So we're going to have now 20 passes there. In principle, the more epochs, the better the algorithm learns. You will see that the loss functions start getting lower and lower values. It means that the training is improving. The network learns more and more information. The batch size is the amount of images we will use in each epoch for the algorithm to learn. We put 64 here. These are hyperparameters. So this typically you want smallish batch sizes, but also depends on the complexity of the model. And to large extent, all these parameters are kind of a trial and error. So, okay, after we can go back on this thing. So let's run the second cell, selecting the simple option. So what is doing here, as we said, here we have a single layer, and this in Keras, this is defined as layers.dense. This is the dense network. And then as human brain works, right, we have a set of inputs. And then if we see something interesting, we activate the neuron. So this is what it does. So this is a ReLU is a rectified linear activation function. It's a non-linear one. So if it passes some threshold, then you know, as human brain, the network fires effectively. And this is for the encoding part. And then for the decoded part, we have an activation, we have a sigmoid. So it will give effectively a probability, a range from 0 to 1. Yeah, as an output. I think, I don't know, Greg, what do you think? But maybe we can discuss later the other configuration.
Yeah, I think we could just, you don't have to do all the examples. I would maybe do
Yes,
multi-layer
because,
with noise and something like that.
Yeah. So let's run once first to see that everything, yes.
Sorry, somebody posted a question saying, is encoding underscore dim the same as the number of hidden nodes in the latent layer on the Q&A?
Yes, here it is. So if Lucas scrolls a little bit up,
Yeah.
you see that we included this one layer with the encoding dimensions. That's in the encoder. So
Yes.
encoder is single layer, decoder is single layer, and encoding dimension is essentially latent space because there's only one layer.
Yeah.
Thank you.
We compress 784 pixels from 28 by 28 image into the 30, whatever, 34.
Yeah, 32.
32.
Yeah.
It's compression factor of nearly 25.
Yeah, so the idea is you have your image, you start compressing it, you collect the most important features, and then you start decompressing, and the output will be the same image as you have as the input. Okay. Okay, then this is the next cell. I mean, we'll stay with the simple one, and then we run the third cell. So this is actually, maybe I can. So actually, this gives us actually a summary of the networks. As we said, we have one input layer. We have the input here, 784 pixels. We decoded 32 with a single dense layer, and then we decode it and go back to the original image. So, and here maybe you can identify some parts, like for instance, what is very important is the loss. Okay, we're going to discuss later. I think, yeah, I don't know. It's a bit, maybe we can run and we'll go back and discuss it later if you have questions, but or when we do a more complicated problem. But here is the point that we are doing the training. So this, okay, sorry, let me, yeah. Here we get the data and we do the training on this cell here. So you see the different epochs. It's going to run to 20 epochs. This is the loss function. This is the accuracy. This is the loss value. So what you see, and this is actually what you would expect actually, is that the loss starts getting lower and lower. So in principle, what it does, it compares with the truth and goes back with the back propagation, improves the parameters, and then we do the training. And yeah, in principle, after a few epochs, we'll start converging, which is, I think, kind of what we see. It started from 0.19 and then it goes down to 0.10, 0.9, and the improvement gradually, it gets smaller and smaller as you go to higher epochs.
So at this point, it stopped training, but it will collect data and do some images. So you'll see how the loss function changes with steps.
So, each epoch is like passing through the entire training data set. Then we update the weights. I mean, the network updates the weights in order to minimize tries to go, imagine as a function in multi dimensions, and then gradually tries to find the minimum. So another thing that we should, tries to find the minimum, and then after passing one time after the entire data set, improves the weight of the network, and then this goes on until, in this case, until reaching 20 epochs. Now, this actually, okay, can you see the plots here? So this shows, the first plot shows the model. Okay, maybe first let's go to the loss. So two things here. The blue line that says train. So what we have the sample that consists of training and testing data. So the training data set, we split the sample in train data set, which is usually the largest fraction of the sample, and another orthogonal set of events, set of images, that is a tensor sample. So what we want to see is actually that what we train on the training sample, and the performance that we get on the training sample is more or less the same as in the tested sample. Now, it's important to check this metric, because if, for instance, we wouldn't do this, we have a problem. We can check if, for instance, it's overfitting. If it learns very well the data that are used for training, but it cannot extrapolate it in unseen data. If this was the case, you would see the testing distribution, the orange one, to be much higher than the blue one. Here, the fact that the orange one is lower than the blue one, it's actually a good thing, and it's probably because we have some dropout. So when we train to avoid overfitting, for instance, we can remove some of the nodes. But when we test it, we include the full capacity of the model, and this gives somewhat better performance for testing. This is great. You see that actually even a couple, 3, 4, 5 epochs, the training reaches kind of it gets very close to the optimal. Maybe if I can take this opportunity, one thing that one could also check, particularly in more challenging problems, is the learning rate. So it's how the steps effectively that the network that the algorithm takes in order to optimize the various weights. So, you know, if you pick very small values of this learning rate, you may end up having ending in a local minimum, and not finding the global minimum will give the optimal result. If you get very large one, you may bounce around your function, but not really reach the local minimum. In real-time application, one technique that one could try is to use a decay learning rate. Start with a relative larger learning rate, and then as you go on with the epochs, start reducing it with some functional form. It can be an exponent, etc. Okay, what else here? The other thing that we could discuss is actually the accuracy, which is actually a metric that measures the proportion of correct predictions among the total number of cases processed. And you see the accuracy increases as one would expect with respect to as a function of the number of epochs, both for the testing and for the training. Sorry, there are some messages.
Yeah, I'm answering.
You respond. Okay. Yes. Yes. I think we can run unless Greg, you want to add something here? We can discuss. You know,
just maybe notice that accuracy is not very good in this case because it's a very simple autoencoder with just one dense layer, and you will see other examples where accuracy is significantly less oscillating and much higher.
Yeah. So yeah, in general, the goal here is to have examples on how to develop these techniques. Usually, you know, to have like a good performance, you need much larger data sets, more complex application. But it's like a recipe, you know. Adding one extra layer is simple, and this is serves as an example here for your actual research projects. Now, running the next one is actually shows the original. I mean, we are trying now actually to predict effectively numbers, right? On the top row are the original numbers, and on the bottom row is the reconstruction, what we achieved by with this auto encoder. So the reconstruction is pretty reasonable. I mean, in more complex numbers, you probably more fuzzy ones, you see there are some, you know, it's more poor the performance. But I mean, we will review again these images, the bottom row, when we have a more complex algorithm. Yeah. I think we can skip these two, and maybe we can try a more complicated algorithm or add noise. In this case, run the same thing, but adding noise.
Or maybe just let's run maybe multi-layer with the noise.
Multi-layer with the noise, yeah. So yeah, let's go back to the first one, the first cell. So we have to change here, and then we have to change, or maybe since it's fast, I would say, okay, let's run the multi-layer one with noise off, just to see what we get, and then we can do it faster now. So effectively, we just have to go to the results. So click run all of the cells. So here you see we increase. So we are talking about here 5 5 layers. Let's see, where is the simple one? Yes, 1, 2, 3, 4, 5, 6 layers. So this is shown. This is useful to understand what the network is doing, how many nodes you have per layer, reported to, etc. I don't think we need to run this. No, we have to run this one. So I assume if you have troubles running the code, you would drop a line. Yeah, there is one question. Yeah, yeah. Okay, yeah, you answered it. And also depends on the task you want to do, if you want to do classification or regression. We do different losses. We use different losses. Okay. So here improved a little bit. Of course, there are some fluctuations that you see here in the testing sample. These are statistical fluctuations. I mean, the testing sample is much smaller, has much less images than the training sample, so that's why it fluctuates more. But in general, you see the blue line improves with respect to the single layer.
Yeah, just to give some idea, this MNIST data set is 10,000 images, and I believe we use 9,000 for training and 1,000 for testing.
Yeah, so for this case, you should not worry like about these fluctuations here. And here you see actually that here, 5 that was more tricky here looks a bit better than what was how it was with a single layer. So now let's repeat this exercise by adding noise with the same, just changing, including noise, make it a little bit more difficult the problem or more difficult the problem. So let me actually keep so let's run all the cells again.
So here, the way we include noise, we basically train on the images to which we added the random Gaussian noise. So random pixels are just lit up with various intensities, and by just Gaussian random noise. And what we do, we feed the autoencoder this corrupted data, but we compare it with the original images without the noise. This way, we teach autoencoder how to ignore the noise, but still not ignore the interesting features of the data set. And you would see quite dramatically how it really cleans up the data. You see that the loss functions is higher than in previous case. It was about 9% because you're now really losing some of the features because you want to remove noise. But that's good.
There is a question, where are the square terms supposed to go in the LLP loss function for weak supervision? So the LLP loss is using the mean square error approach, right? And I think, if I remember correctly, is the sum. So you have like the you go in batches. You have the you have one is the predicted. You have the predicted portion, which is sorry. Okay, there keep coming questions, but let me answer this. So there is like you have the prediction minus what the truth. This is square, and this all is within a sum across all your batches and divided by the number of batches. Should be something like this. So it's there where the square goes.
Right. Actually, I looked at the original paper. My original formula was correct. So the LLP loss they used, they didn't have squares. They just had.
Oh, they didn't have in the origin. Okay.
So I'll correct my slides back.
So there is one question. Can we don't get exactly the same curve as mine? I don't think there is some. Well, the events, the weights. So there could be some effect from. It should be very similar though, right? Because the weights are initialized. There is some randomness. There is some, the initialization of the weights is random. So this could cause some difference in the accuracy or the loss. But I would believe this is at the beginning. Then after you train a few epochs, it should be very, very similar. Yes, you mentioned yes, initiate and different. This could be, but it should show up at the very beginning, at the very like the first few epochs, not at the end. So here you see, we are actually seeing it from the printout, but here you see that actually the accuracy gets it's higher, it's larger. Also, the loss plateaus at higher values, which is expected. And this is how the image looks like with noise, right? So we give a more difficult problem, but nevertheless, it seems that the algorithm is able to understand to figure out the important features and don't mess up actually the prediction with respect to the noise. So maybe shall we?
I would say let's do maybe variational and then switch to the second notebook.
Yes.
Variational, we could just maybe point out where this KL loss function is coded.
Yes. So yeah, let's do variational. So let's start running and
maybe without noise so that we don't
without,
confuse.
yes, without noise. I think here, there's not much to add here with respect to what Greg discussed in his slides. Here we have
Here we
patterns.
chose
Usually it's Gaussian, you have the mean and you have the sigma.
We chose two latent dimensions so that we could visualize the latent space. So latent space, because now it's not a point, it's a whole function distribution. Each point is encoded as the distribution. So you really have a two-dimensional space, X and Y, think about this. So we encode everything in this two-dimensional space.
Yeah. Okay, and this is much more complex now, but let's take it like try to I mean, the concept the same, but the other thing is that we try now, we use this KL, the KL divergence. So we effectively think you have two distributions, and you want with this KL, this loss function using the KL criteria is to minimize, to optimize the weights of the network by minimizing the distance between the two distributions. Is effectively what the KL does. So it's a metric of how different are two distributions.
So you minimize both the reconstruction loss, which is just how well you reproduce the image, but the second term, realization term, tells you that we want two Gaussians to be close to each other.
Yes.
But basically, that ensures continuity of the space, two spatially close, two images which have very similar features would end up with very similar encoded distributions.
Yeah.
And this is just the KL loss for Gaussian distribution, the formula I gave you on the transparency.
Yeah, and this is actually, as we discussed earlier, but now the network is much more complicated. So this is actually particularly useful in more complicated networks to figure out effectively, also to spot issues on the design, understand how the network works here. Now, let's run also the steps and the train. Take a bit more time. I removed the noise, right? Yes.
Yes, you did. Yes. Now the loss is very different here because the loss has this significant KL component. So it doesn't have the interpretation of the reconstruction area, some average between the two terms. It's important that it decreases, but the absolute value is not so.
Yeah. There's also another question. Can you use a model that is trained on no noise data and predict the noisy data? Yeah, so this goes more on the anomaly detection. I mean, for instance, in experiments, Greg actually gave an example. I mean, you train on a hypothesis that you know, on the background, for instance, a process that you know or processes or jets that you know well, and then you try to look for something that is abnormal. This could be because it's a jet structure, for instance, that we haven't thought or is not in the physics we know. It's called the standard model of particle physics. We also try these things to spot malfunction on the detector, for instance. You train using let's say data taking periods that you know that the detector works well, and then you test it on data taking periods that we haven't seen. We call it runs. I mean, and if it is something differences, I mean, depends also, you have to, the region you select on the loss function, then you pay more attention on the specific part of the detector. So yes, this is something that, yeah, we do. I mean, if you train on non-noisy data,
yeah, you could try. I mean, just
yes.
play around with this. Just swap out noise and no noise.
Yeah.
It probably would generate some noise. I haven't tried this, but yeah.
Yeah.
Interesting exercise.
Yeah, I mean, this is again the model accuracy and the loss, as Greg said, improves. Improves, but also for the reason that Greg mentioned, effectively it's at much higher values.
Here, 20 steps probably are not quite enough. You see that we're still decreasing.
It doesn't reach a plateau yet. So
you see there's some errors. 4 is be constructed as 9, for instance.
yes.
But if you train a little bit more, you would actually have better. I know that when I run it with 50 steps, it was much more accurate.
Yeah. Here, the 9 here could be as maybe, I'm not sure if it's 9 or 7.
Yeah.
It's
But let's see, because the color maps are really
yeah. So this effectively shows you there should be like 10 classes, right? 10 categories, but it doesn't know a priori how many are the categories. So what it does, it clusters, it positions in this two-dimensional plot different numbers to different areas. So in a nutshell, what it does identify that the different numbers have different features. And you could think, okay, we do it with numbers, but someone, for instance, I don't know, in problems, could be even unrelated to physics. If you have different cases, a priori, you don't know how many cases you have, and you want to classify, you have like, I don't know, different animals, cows, dogs, cats, or something else. Then you can use this code and it will create clusters of points, clusters of images in different regions. And yeah, I mean, this is a kind of, you can think about also as a clustering problem, for instance. Now, of course, I believe, for instance, 4 and 9 could be close to each other here because there is some confusion. I mean, those that are closer, the algorithm has some more difficulty to separate them. Would be interesting to see how this image improves it should improve. I mean, Greg tried it up to 50 epochs, but if you want to play, I mean, later in your free time, you can train it with more epochs and see that actually these different colors, these different clusters become more and more distinct. Yes, so I think this is the same dimensions, yes, exactly, as as what we see here. So
Yeah,
in
except that
principle,
there is minus. So the problem is that the way this image is created, you cannot easily plot them so that they correspond exactly to the map. So the -4 is at the top here, and +4.
yes, it's just yeah.
Essentially, you could compare, let's say, where these sevens are concentrated. So that's x of around -4, -3, and y's of the order of 0 near 0. So we could go back to the color image and look at -3 and around 0, and you see this violet cluster, which is 7. So that allows you just so what this manifold you see at the bottom, essentially we take a rectangular grid over the entire space -4 to 4, and some of this is not even populated by the trained data, but we generate images which kind of merge from one digit to another. And this is not very visible here because the training wasn't sufficient, but if you train for 50 epochs, you see very well how 9 becomes 3 and 3 becomes 8 and all this position. So this is how you could, if you have cluster of cats, cluster of dogs, you could take a point in between and would be cat, which looks like a dog or something similar. Or you could create some artificial animal by picking a point which wasn't even occupied by the trained data. So that's how people generate images.
Yeah. Then you start here, there is some confusion. This will start clearing up the tree if you run with more epochs. It's kind of cool to see this.
But the interesting thing that it generates the images which it never saw.
Never seen, yes.
So I think now we have 25 minutes left. We could do the other notebook.
Yes.
Because that's interesting. That's really anomaly detection.
Yeah. So let's open the next one. So you have to disconnect, and I think you can delete the runtime and no, here, yeah, here. So okay, yeah, when you try to run it all, you will ask to disconnect runtime. You just feel free to terminate other sessions and focus on
Just
the
limited
anomaly.
resources on Google Colab. They don't allow you to run too many sessions.
So assuming, everybody is in the other notebook, let's start running it here. Okay, so here it's kind of related to a question that was, I don't remember the name, but if we train on something and then predict on something else, for instance, or, how it would be classified. Here we train on process that we know and try to see, we compare the reconstruction loss, and if there are differences, this is kind of an anomaly, something that we were not expecting or the network hasn't seen. And yeah, let's keep here. So here again, the first cell, we use the first cell to define the configuration, the various options. Let's keep the simpler one, which is with dense layers. The second one is to get the data sets, training and the testing, that we split them. We create the images. So we have a random image, we have a shoe, and then we have a sweater.
So these are anomalies. So we train on
Yes.
these same digits as before. So it learns
Yes.
how to find zeros, ones, and nines. And then we confuse it by throwing an image of a shoe or an image of a sweater into
Yeah.
this. And let's see if it finds them anomalous or not.
Yeah. So then on the output, depend where we select, we will, we look more or less anomalous events or images, let's say. So this is run. No, to run this. Okay. So here where we create auto encoders, this is very similar to what we were discussing earlier, so we can skip it. Maybe when we run again with the CNNs, with the convolutional networks, just go very briefly here and discuss a couple of things. So these are similar things, some parameters of our algorithm. The simple dense network. The laws, metrics that we use, and here is the training. Here are 30 epochs. Remember, we are using the same input data set as in the previous exercise, right? Which is numbers from 0 to 9. And while we are waiting, okay, it's almost done. Just to tell you, now here you see the accuracy, fine. That shouldn't be different really from the previous one. The difference here is coming on this part here, where what we do is actually in these lines, we we evaluate, actually, calculate the reconstruction error that you see as RE here for its test image, right? So in principle, this is the square difference between the original and the constructed images that you see. Well, you didn't put square. I know you put squares, right? Yes, for the convolution one. And yeah, so the largest errors we have, this means that we have anomalous images, which in our case would be a shoe or a coat or a jacket. So I did run this? No, it was from before. Okay,
This
so
is the
here
anomaly score.
yeah, so this is the anomaly score. So what we do in practice, so these are cases that the reconstruction error is very small. So it means that probably these are images that the algorithm was trained on. The higher we go to the reconstruction error, this would be like images that look more like anomalies, not seen, the algorithm hasn't seen. Of course, you have to train more images and you will see a distribution here. Okay. And here are the largest reconstruction errors that you can see visually in this plot here. And actually, you can see, which kind of makes sense, probably the shoe has actually smaller average reconstruction error than the sweater. In this case, we can cheat. We know which are the images, and we can see actually. So it's easier for the algorithm to discriminate between sweater and numbers than shoe and numbers. And let's run this also cell. So this is actually what will be the original image. The worst one and the reconstructed one. So of course, we train with 30 epochs. It's a simple network with just 10K events, but you see actually that it works pretty well to figure out also the worstest images. So the number, in the case the third worst is a number, a shoe. Yeah, okay, it looks like a shoe with some imagination, and sweater. Yes. So maybe we can run also the CNN in the.
Yeah, we could run a CNN and see
Yes.
what happens.
Yeah. I think conv should work, but okay.
Conf would be enough.
Yeah, yeah. So let's run the cells. I just want to make a couple of comments. So these are the same things. You will see the same things here. So here I just want to make a couple of comments. Here is where we define the convolutional neural network. So we have the image, we define a path. We define the number of filters we have. Then one thing that we do is actually, for instance, this is more like based on experience. You see that here after the first convolution layer, we don't put the second, we put a max pooling. So what we do is we define a window. In this case, it's a 2x2. You have the image. After the convolution, we downscales the image size. Then we put a max pooling in 2x2. The reason we do, there are a couple of reasons. First of all, usually when we have images, to avoid picking on irrelevant features, we do some pre-processing. We rotate them, we translate them, etc. Doing max pooling, first of all, makes the training not so sensitive on this on small differences between the input images. The second thing is that you can do what we do with pooling is imagine the image has some numbers. So when in a 2x2 windows, in this case, we can pick, for instance, the sum, we can pick the maximum, we can pick the minimum of all these numbers. This allows us to reduce the dimensionality, but also focus on more important features of this 2x2, in this case, window, and makes also the network more robust. avoids overtraining, for instance. So this is why it's a good advice to use max pooling before running the second convolutional layer. So just something based on experience. Similarly, this is when we are encoding the image, and here we are decoding the image. The same concept as we were doing up to now.
Except that now you upsample rather than
You upsample. Now you have to make, yes, exactly. The image go back to the original dimension, effectively. And you can actually see all these things better. We have a 28 by 28 image here. Then we go 14 times 14, blah, blah, blah. And then we start upsampling again.
So now you see that accuracy is really pretty high. It's pretty close to 1. So this is the case where accuracy is really very good, because convolutional networks are very good for processing images. They basically operate like images because they have pixels. Their neurons are pixels of the image. So you see that accuracy is much better, and you'll see the plot which shows that it's pretty healthy.
Yeah, and you see now, actually, you were seeing here, but you see also visually here how much improved, and the loss much smaller value. So, and this is the reconstruction error here.
So you see now Shu is not really an anomaly.
Yeah.
It's hidden somewhere in the middle of the
Yeah,
distribution.
because you see the mean value here for the shoe is much closer. I think it was 0.05 before, and the sweater was
0.10.
0.010. Now it's a factor of 2 or more closer to. Yeah.
So Shu is not found as an anomaly anymore. That tells you that you have to be careful. I mean, it's clearly an anomaly, but not with this training.
Yes.
Couple of digits are rather
Yes.
poor, but they're still nicely reconstructed, and sweater is not reconstructed at all.
Yeah. Now there could be many reasons. I mean, I don't know if in this data set we're using there is some pre-processing. Also, you need many more images, and probably, yeah. But this is something also, you have the code, you can consider it as a challenge actually to try to improve this and play.
Try to maybe find cats among dogs, because there are many of these MNIST data sets, so you could get sets of specific animals or specific flowers. Not all of them are 28 by 28 pixels, so you might need to change the dimensionality of your whole thing. But if you work with MNIST data sets, we use just 2 fashion for the shoe and sweater, and digits for the other one. You could try to train on fashion images and then see if you could recognize, distinguish shoes from shorts, things like that. So there are infinite amount of things you could do and play around.
Yeah. Do you have any questions? So I haven't checked the chat for a while.
Yeah, I'm looking at the chat.
Okay, thanks. Thanks, Greg.
Yes.
Yeah, it's difficult because I have a phone.
Yeah, it's too hard to do both.
Yeah, and some on my laptop. So yeah.
So there's a question if the reconstruction error of the anomaly shoes and shorts is even lower than normal, how is this model useful? Well, that's the big problem with this anomaly detection, because you don't really have probabilistic way of saying, how often you would detect something as an anomaly. This is because of this Pearson theorem. So you could only compare two things in a proper way with probabilistic interpretation. All that anomaly detection does, it tells you that certain images do not look like they come from the training sample. And it's very hard to say why. So you saw that the simple network seems to identify the shoes and the sweater as correct two outliers, but more complicated network, for instance, didn't think that shoe is an outlier. And we don't know why, right? Because we don't really know the intrinsic of this latent space. If you use variation autoencoder for this problem, which you could do, you could just replace convolutional with variational from the previous exercise, then you could open the latent space and see what's going on. So you would see where it would put the shoe, where it would put the sweater with respect to the digits. And there you could try to figure out how to change the network to make it more prone against errors like calling shoe a number. But there's a lot of things you could do just by playing. This is simple examples which we just used so that they run in finite time to show you few various options and just bring this idea of autoencoders, which is very powerful tool, and anomaly detection.
Yeah. Yeah, I mean, you could use more filters because now you don't know, maybe it just looks for circles or some smooth angles. I mean, we don't have so many filters there, so it could be and confuses the shoe with some digits. So there is a lot of
Number 7 or something, or 4,
yeah,
which has a little bit similarity in shape.
yeah. Because depends how you do it, the filter is just numbers that you multiply, you make this gray scale. It's a scale from 0, each pixel has a value from 0 to 1, and then you slide the pixel, the parts, I mean the convolutional kernel across the image, which has some numbers. Could be 0, 1, 0, 0, for instance, to pick some edges, and you multiply this, and then has a new image after convolution. So, but each filter is designed to get to identify different features, and you have to just one thing is to put more filters. I think it would be a nice exercise to play with.
So a lot of this is really trial and error, because unfortunately we don't really have a good theory of machine learning training. This is an interesting statistical mechanics problem which some people are trying to solve. But so far there's a lot of black magic there. So you try this, and it's well known that certain configurations are more stable for certain problems. So that's how people figure out, this max pooling, what kind of loss functions you use for what kind of problems. A lot of this is just know-how which you learn by just doing and running different examples. So I think Rick wants us to wrap things up, which is about time to do, right? We have 5 minutes.
Thank you. Really appreciate everything you've done. So please do let us know on Slack if you have any issues with access or anything that we need to refocus on. because I think we tend to lose the questions from the Zoom. Actually, I do see there's an open question on the Q&A system saying, if I understand correctly, encoding and decoding ... That may be one that you want to address quickly. But just before you do that, I just wanted to say to people, yes, do use the Slack link if you're having any support issues. We can try to address them there.
Yeah, so I
So
try answering this question, Rick, very quickly. So the question was that encoding and decoding could be any function and inverse function respectively. Do you think it's possible to encode and learn from a data set by going to a different space, for instance, Fourier space? I'm especially interested in using autoencoders in astronomy, where working in frequency space has a better chance of separating signal in the background. Yeah, I suppose this is possible. In fact, you don't even have to have decoder and encoder with very similar architecture. As long as you match dimensions, you could imagine that encoder and decoder could have different dense layers, number of layers, because the training would make things work as correctly as possible. You would find that certain decoding functions and encoding functions are just much more powerful for your problem. But indeed, working with Fourier space is perfectly fine. But for that, you don't really need machine learning. You just basically, instead of images, give Fourier samples. The images, anyway, for the convolutional network, we use them as images. But for dense layers, we flatten them. So we flatten them in one-dimensional array of 784 numbers. So you could certainly do Fourier transform beforehand if you want to. The neural net wouldn't care what your inputs are as long as they're properly normalized. Usually it's a good idea just to normalize numbers between 0 and 1 to make it easier for the network. But other than that, you could use any set. And there was second, apologies if this was already answered. What is the proportion of anomalies to missed digits in the test data set? None. So for testing and for training, we only use digits. There was no fashion. So fashions were these two fashion thing, the shoe and the sweater, the decoder never saw, encoder and decoder never saw. So we just train it on digits data set, pure digits, no anomalies, and then we throw these two anomalies. But I bet you if you throw a couple of these extra images in the training data set, you won't be changing much, because that's exactly why we could apply this on a sample with large background but small amount of signal, because the dimensionality reduction ensures that you pick only on the most important, most frequent features of your training data set, and having a very small proportion of the signal wouldn't mess things up.
Like that's why you reweight your signal and background when you do classifications to have relatively similar populations, right? Having a small fraction, it wouldn't matter.
Okay, I think we should wrap up there. We're at the half hour. Thank you again, Lucas and Greg, so much. We will meet again in an hour and a half. This time we're going to look at machine learning applied directly to the first stars of the universe and their effect. It relates to 21 centimeter astronomy. But again, I hope it will be a useful example for you all to understand how best to apply machine learning in another new situation. But anyway, thank you again, everybody. We're going to take this Zoom offline now, and it'll come back up